Right, so I guess, yes, we can start. Thank you very much for starting the recording. And so it's my pleasure for the last session for today to let the floor to Valeriy Bardakov from the Sobolev Institute of Mathematics, and he will speak about Rota-Baxter operators on groups, racks, and algebras.
Oh, thank you, thank you. At first, I would like to thank the organizers of this very nice activity for the invitation and for the possibility to give a talk. Today, I will speak about Rota-Baxter operators on different algebraic systems, on algebras, on groups and Hopf algebra, and I will try to define some operators, Rota-Baxter operators and averaging operators on rack and on the quandles. I will speak about some results which we have found with my colleagues during during last years. And I divide my talk on 4 parts. In the first part, I will discuss algebraic Rota-Baxter operators and different connections between them. On the second part, we will discuss Rota-Baxter operators on group. And the third part, we discuss Rota-Baxter operators on the Hopf algebra, and the last part is dedicated to the different operators on racks and quandles. And I start with the definition of algebra Rota-Baxter operators, and the following definition you can find in the paper of Baxter in 1960, and the definition is the following. Suppose that we have some algebra A. A is an algebra over a field K. When a linear operator A on algebra A is called a Rota-Baxter operator of weight lambda, where lambda is some elements from the K, such that the following equality hold. If we consider the product A of A and A of B, when it's equal to image A of this sum. Here we have A product B, A of B, and here we have lambda multiplied to the product AB. And if we have an algebra with some Rota-Baxter operator, when we will call this algebra a Rota-Baxter algebra. And you can see that this definition on arbitrary algebra, it can be associative Lie algebra, and so on. And now it's interesting to consider the following possibility. Suppose that we have an A be an associative algebra when we can find and its associative algebra Rota-Baxter operators. After this, we can construct on A so-called Lie algebra, A with minus, and define the Rota-Baxter operators on this Lie algebra. And the third possibility, we can construct on associative algebra a Jordan algebra as A with plus, and study Rota-Baxter operators on this Jordan algebra. And it's interesting to study the following questions. Are there some connections between these operators? Because we have 3 sets of operators, of course, it's not difficult to prove the following proposition. Proposition is the following. If we have associative algebra Rota-Baxter operator on A, when this operator induces a Rota-Baxter operator on Lie algebra, A with minus, and is Jordan algebra Rota-Baxter operator on A with plus. And as example, we will consider the famous Swidler algebra H4. This algebra is the famous because it's the simplest example of non-commutative 4-dimensional Hopf algebra. And I recall that with algebra is generated by two elements x and g with the following multiplication: g square is equal to 1. Hence, we have a cyclic group of order 2, what is generated by element g. Also, we have element x, such that x square is equal to 0. And we have multiplication of the following form: xg is equal to minus gx. Hence, this algebra as vector space is four-dimensional vector space, and on this vector space we can define a multiplication, co-unit, and antipode by the following proof, where co-multiplication on G is equal to G and the O times G, because G is group-like elements, and for element A co-multiplications is defined by the following rule, and the delta of Gx defined by the following formula. Co-units is defined by the rule of operator. We have 8 Rota-Baxter operators. Because it's linear, it's enough to define these operators on basis elements. And you can see that we don't have operators such that the dimension of kernel is equal to 3. And its last operators, and we can see that this list of Rota-Baxter operators is not full, as I told that this list does not contain an operators with three-dimensional kernel. And Maxim Podkorytov constructed example of the following operators. Let us define a new basis. Now we consider a basis of H4 with elements 1, G, and instead X and GX. Let us take the element E and F. When we have operator A such that the image of A of elements 1, E at F is 0, and the image of G is the following linear combination. And it's not difficult to check that this operator is a Rota-Baxter operator on algebra H4. We study the Rota-Baxter operators on associative algebra H4, and now it's interesting to find Lie algebra Rota-Baxter operators on algebra H4 with minus. It's the Lie algebra, and in our paper with Igor Nikonov and Viktor Nikolaevich Zhelyabin, we given a complete description of Lie algebra Rota-Baxter operators. I hope that it's full list. This list of Lie algebra Rota-Baxter operators contains 48 operators. Of course, I will not give a full description of these operators, but now I formulate only one theorem. We consider the Lie algebra Rota-Baxter operators such that dimension of the kernel is equal to 3. If we have the basis in the as on the previous slide with basis element 1, G, E, and F, then it's possible to prove the following theorem. Suppose that dimension of operator kernel of the operator A is equal to 3, when we have following two types of Rota-Baxter operators. First type R of 1, it's the linear combination of this basis element. R of G is equal to minus lambda multiplied on R1, and image of E and F is equal to 0. It's easy to see that the kernel of dimension of the kernel this operation is equal to 3. And the second type of operator is the following. Image of 1 is equal to 0. Here it's the image of G defined by the following formula. Image of E is equal to 0. And here we have the image of F with some condition of parameters. And now we are going to definition of group Rota-Baxter operators. The group Rota-Baxter operators were defined in the paper of Go, Lang, and Sheng, and they give the following two definitions. They defined the Rota-Baxter operators of weight 1 and Rota-Baxter operators of weight minus 1 on arbitrary group. Suppose the G be an arbitrary group and the map B from G to G it's called a Rota-Baxter operator of weight 1 if the following equality holds. Have a look. Here we have in the left-hand side, we have the product B of G and B of H, and have a look on this product in the right-hand side. Here we have conjugation of elements G by element B of G inverse and multiply to element G. This is the definition of Rota-Baxter operator of weight 1. And the second definition is the definition of Rota-Baxter operator of weight minus 1. It's look like similar, but in the right half side, we have the conjugation of elements H by element C G inverse, and we multiply to element G with the right hand side. This is two definition, and there is a bijection between Rota-Baxter operators of weight 1 and weight minus 1 on arbitrary group. This bijection is defined by the following formula, and we will consider the Rota-Baxter operators of weight 1 and will speak simply about Rota-Baxter operator. We will denote it G, that means group Rota-Baxter operator. And if we have a group with Rota-Baxter operator, then we will say about Rota-Baxter group. And now I formulated the first example. The first examples are the following. Suppose that G is an arbitrary group, when if we send any element G to the unit element, then we will denote this operator by B sub 0, and it's not difficult to see that this is Rota-Baxter operator on G. And the second type of operator, B with minus 1, it send any element G to its inverse. It's the second type of Rota-Baxter operator. These two type of operator you can define on arbitrary group, and these operators we will call by elementary Rota-Baxter operators. And the following result you can find in the paper of three authors, Go, Lang, and Sheng. This is the following property of arbitrary Rota-Baxter operator. Arbitrary Rota-Baxter operator on group send unit element to the unit element, and the kernel of this operator is subgroup of G, and the image B, it's also subgroup of the group G. And the main property of Rota-Baxter operator, suppose that we have group G on which we defined a Rota-Baxter operator, when we can define new operator G circle H, which is defined by the following formula. You remember this formula from the definition of Rota-Baxter operator of weight 1. And if we consider the set G with this operator circle, then we will have a group. And if we consider the operator B, the same operator which we define on the group G with multiplication point, then B is a Rota-Baxter operator on the group G with the circle. And the map B from G with circle to G with points, it's a homomorphism of Rota-Baxter group. This theorem is analog of theorem for the algebras. And we can formulate the general problem about description of Rota-Baxter operators on group. The general problem is the following. Suppose that we have some group. Can we describe all Rota-Baxter operators on this group? We don't have a full solution of this problem. We can full description Rota-Baxter operators only for abelian group. For abelian group, we have the following result. If G is abelian group, when B is a Rota-Baxter operator on G, if and only if B is an endomorphism of the group G. Also not difficult to prove the following proposition. Suppose that G and B be a Rota-Baxter group, and B is an automorphism of group G, when G is abelian group. And also the second part of this proposition gives possibility to construct some type of Rota-Baxter operators. Suppose that we have H is an abelian subgroup of a group G, when any homomorphism or anti-homomorphism from B from group G to H is a Rota-Baxter operator. Also, it's possible to suggest another possibility for construct a Rota-Baxter operator. At first, I introduce some definition. A group G is called factorizable if G is a product of two subgroup H and L. For some, it's subgroup H and L. And if in addition the intersection of two subgroup is the trivial subgroup, when such factorization it's called exact. And if H and L are proper subgroups of G, we will call this factorization G is equal to H and L as proper factorization. And using factorization, you can find the next example in the paper of GLS, and this example gives a possibility to construct Rota-Baxter operators which are not elementary. Example is the following. Let G be a group given an exact factorization, when we can define a map B from G to G by the following formula. B acts on the product H and L, it's equal to L inverse. When this map is a Rota-Baxter operator on group G. And it's interesting to formulate the following question. We know definition of group Rota-Baxter operators of weight 1 and weight -1, and we can formulate the question, let lambda be a real number. Is it possible to define on a group G a Rota-Baxter operator of weight lambda? for lambda it's equal to 0, this question was formulated in the following paper of four authors, Go, Gu, Lin, and Zhu. And we study this question, and it's not difficult to prove the following proposition. Suppose that G be a group and F is some map from G to G, which is bijection, when we can define a new operation on a group G such that A star B is equal to F inverse, because F is bijection, we can define this map. We consider the product F A and FB. We take the product in the group G and take F inverse. When we have a group operation on a set G. In particular, suppose that lambda is real number which is different from zero, and G is a group such that the map F, which defined by the formula F of G is equal to G, and here in p power lambda is a well-defined bijection on a group G. When in this case G star H is equal to the following product, and this is group operation on G, and we can give the following definition. Let lambda is a real non-zero number and G be a group such that the map F, which is defined by the following formula, is well-defined bijection. In this case, a map B from G to G is said to be a Rota-Baxter operator of weight lambda if B satisfies the following equality. You can see that if we take lambda is equal to 1, when we get a Rota-Baxter operator of weight 1, if we take lambda is minus 1, we will get the Rota-Baxter operator of weight minus 1. And we know connection between Rota-Baxter operators on group and Rota-Baxter operators on Lie algebra, and we can prove the following theorem. Let B be a Rota-Baxter operator of weight lambda, which is not equal to 0 on a Lie group G, and be calligraphic. It's a differential of at the unit of the group G. When this operator is a Rota-Baxter operator of weight lambda on the Lie algebra G, which is Lie algebra, what is correspond to the group G. You remember that on the Lie algebra we can define the operator Rota-Baxter of arbitrary weight. And it's interesting to understand connection between a group Rota-Baxter operators and the algebra Rota-Baxter operator. In the paper of all three these three authors, it was proved that a group Rota-Baxter operator on a Lie group induces an algebra Rota-Baxter operator on the corresponding Lie algebra. It means that in some sense, this definition of Rota-Baxter operator on group, it's a good definition. Also, in our paper with Всеволод Губарев, we proved that if we have a Rota-Baxter group with Rota-Baxter operator, when we can construct a Lie algebra using the lower central series, we consider the lower central series, take its quotient of this group G by the terms of the lower central series, and define a Lie algebra. which is so-called associated Lie algebra, when this operator B induces an algebra Rota-Baxter operator on this Lie algebra. This is connection between these two type of operators. And now I am going for definition of Hopf Rota-Baxter operators. And I recall the definition which gave Maxim Goncharov. And the definition is the following. Suppose that H be a co-commutative Hopf algebra, and operator B from H to E to H, which is co-algebra homomorphism, and satisfy the following identity, you can see that it's look like as a group operator of weight lambda of weight 1, but now we use the co-multiplication. Delta of A is equal to tensor product A1 and A2. We will use Swidler notation here. Delta square is the product of free element, and a linear operator B from H to H, which satisfy the equality 1, is called a co-commutative Hopf Rota-Baxter operator. We will simply say about Hopf Rota-Baxter operator. In particular, if G is a group-like element, in this case, we have that A is equal to A sub 1, A sub 2, A sub 3, and then antipode SA is equal to A inverse, and we have the following formula, but you can see that this is the definition of Rota-Baxter operator on groups. Hence, the definition of Maxim Goncharov generalizes a definition of Rota-Baxter operator on group, and also it generalizes definition of Rota-Baxter operators on Lie algebra of weight 1. Also, we introduce some definition of Rota-Baxter operator, which possible to use on arbitrary Hopf algebra, but here its condition more complicated. I give the definition. Definition is the following. Suppose that we have some Hopf algebra with multiplication, co-multiplication, co-unit, and antipode. And suppose that the next conditions holds. We have a map B from the H to H opposite with algebra with opposite multiplication is co-algebra homomorphism, and for any element A and B holds the following formula. And third condition, for any element A, B from H holds the following equation. When in this case, we will say that B is to be a non-commutative Hopf Rota-Baxter operator. And it's possible to prove that using with Rota-Baxter operator, we can define new Hopf algebra. And now I will discuss about different type of Rota-Baxter operators. We know different Rota-Baxter operators on algebras, on group, on Hopf algebras. On Hopf algebras, we have two type of Rota-Baxter operators, co-commutative and non-co-commutative. And on some algebras, it's possible to define different types of Rota-Baxter operators. For example, if we have a group G, when we can construct a group algebra K of G, when we can extend by linearity a group Rota-Baxter operator from G to algebra group algebra K of G. It's the first possibility to define a Rota-Baxter operator. The second one, we can assume that this algebra is an associative algebra and find algebra Rota-Baxter operators as on non-associative algebras. And the third possibility, we can assume that K of G is a Hopf algebra and find a Rota-Baxter operators on co-commutative Hopf algebras. And we can formulate the general question. Suppose that on algebraic system 8 are defined different types of Rota-Baxter operators. The first question, how are these operators related? And the second one, second question, which operators belong to different classes at the same time? We are studying this question for our algebra H4, and you remember that if we consider the algebra H4, when elements A and G generate it's a cyclic group of order 2, on cyclic group we have two Rota-Baxter operator. B0 send any element to the element 1, and interesting is it possible to extend this group Rota-Baxter to the Hopf Rota-Baxter operator on this algebra H4? And if characteristic K is equal to, we prove with Igor Nikonov and Viktor Zhelyabin the following result. If characteristic of our field is equal to, when we can construct this extension and we get the Hopf Rota-Baxter operators, which is defined by the following group. If characteristic K is not equal to, when we have a Hopf Rota-Baxter operator on H4, we have two types of operators which is defined by the following formula. And also we can consider instead of operator B0, operator B minus 1. B minus 1 send any element to its inverse element. And we prove the following theorem. If characteristic K is equal to, when we have a Hopf Rota-Baxter operator on H4, which is extension of group Rota-Baxter operator B minus 1. B minus 1 sends element 1 to 1, and B minus 1 send G to element G, because G is the same as its inverse. And we can define this operator on X and Gx by the following formula. And if characteristic K is not equal to, when we have three types of Hopf Rota-Baxter operators, which are extension of group operator B minus 1. And now we know that from the result of Maxim Goncharov, if H be a co-commutative Hopf algebra, when Rota-Baxter Hopf Rota-Baxter operator B from H to H is a co-algebra homomorphism. But if we consider H, which is non-co-commutative old algebra, when it's in general case, it's false. Because we can construct the following example. Let A1 it's not equal to 0, and we can take one Hopf Rota-Baxter operator, which we defined on H4, with X by the following rule on the basis element. You can see that it's extension of B0. We have this Rota-Baxter operator, but if we calculate delta B of X, when this composition contain a monomial of this form, G tensor product of G with coefficients A1. But on the other hand, if we consider the following, calculate the following composition, when this composition does not contain this monomial, hence we don't have this equality. And now we are consider the connection between Hopf Rota-Baxter operator and Lie algebra of Rota-Baxter operators. Here we have the following proposition with Igor Nikonov and Viktor Zhelyabin, and this proposition is the following. Suppose what characteristic of K it's not equal to when for any lambda and A from K, the following map which send B0, which define extension of B0 and B0 of x and B0 of gx is equal to these elements, when this is a Lie algebra Rota-Baxter operator of weight lambda on the Lie algebra H4 with minus. Hence, we take group Rota-Baxter operator, extend this group Rota-Baxter operator to Hopf Rota-Baxter operator, and prove that in fact this Hopf Rota-Baxter operator is Lie algebra Rota-Baxter operator. This is first type of operator, and now we have the second type of operator of the same type. And now we consider connection between group Rota-Baxter operators and algebra Rota-Baxter operators. We prove the following proposition. Let B be a group Rota-Baxter operator on a group G, when B is an algebra Rota-Baxter operator of weight lambda on the group algebra K of G, if and only if lambda is equal to -1, and for any element GH from G, we have this system of equalities of the second type of equalities. And now we consider the connection between group Rota-Baxter operators and the algebra Rota-Baxter operators on arbitrary group G. Suppose that B be a group Rota-Baxter operator, and we denote by H it's the image of this operator, and K is the kernel of this operator. As we know, these are subgroups of G. When we have proved the following theorem, let G be a group and algebra Rota-Baxter operator on group G, when G is the exact factorization of the image of B and the kernel of B, and action of B on K and H is equal to H for any element K from K and H from H. H is commutative group, and the H square lies in normalizer of subgroup K. And conversely, for any exact group factorization G such that H is commutative and the H square lies in the normalizer for any element H in H, the operator, which is defined by the following formula, is a group and algebra Rota-Baxter operator on G and only L on associative algebra K of G. And now I am consider the last part of my talk. I will discuss about averaging and Rota-Baxter operators on rect and quandle. In the talks of Mahender Singh, he gave a very good explanation about quandle, rect, and V.A connection with the knot theory, and I can say only that with quandle were introduced by Joyce and Matveyev, and quandles are, in some sense, a full knot invariant. And the definition is the following. Before defined a quandle, I give a definition of rect. A rect is an empty set X with a binary operation A star B, which satisfies the following axiom. The first axiom: for any element a, b of x, there is a unique element c in x such that a is the product C star B. And the second axiom R2, it's the so-called self-distributivity. We have the following product and this equal to the product of this type. This is the definition of rect. A quandle X is a rect if it satisfies the following axiom. A star A is equal to it. It means that any element of X is idempotent. And suppose that X be a rect, when for any element A in X, we can define a map as sub A such that it sends any element X to the element X star A. And now we denote the image of element X under the action of Si as X star A. We will call this map SA the symmetry at A. It's not difficult to prove the following proposition, but for every element A in X, the symmetry SA is an automorphism of rect X. And the definition, the subgroup of group of automorphism, what is generated by all symmetries, is called the group of inner automorphism and is denoted by in X. This is the neat definition, and also using the first axiom, it follows to give the second operation on the rect. It's the operation which is inverse to the operation star. Star inverse is defined by the following formula. A is equal, if A is equal to C star B, when we define the new operation by the formula C is equal to A star with inverse and with minus 1B. And not different to C, that is equivalent to the, if we consider A star B and here inverse operation on B when we have this element A. And the same if we consider this operation in the different order. Also, it's not difficult to see from axiom R2 the following identities which are equivalent to distributivity axioms. Now we can give a second definition of rect, which include two operators, star and star with minus 1. Such what R1 with prime, we have the analog of the first axiom, and the second axiom is self-distributivity. And now we can give a definition of quandle. Quandles, the first example, it's the trivial quandle. The trivial quandle, it's the quandle with multiplication A star B, it's equal to A. And as we see, the arbitrary trivial quandle can contain arbitrary number of elements. And also, for any group, we can define the different type of quandle. Mahinder defined the conjugacy quandle. Now we can give some generalization of conjugacy quandle. This is so-called end conjugation quandle, which is conjugation by element B in the power n. This is inverse operation, and if n is equal to 1, we have a conjugation quandle. Now we have the definition of core quandle, and we want to construct some extension, some definition of rect extension. Of course, in literature, you can find a lot of definition of this type, but we want to construct some extension which is look like as a group semi-direct product. And suppose that we have two rects, X with multiplication point and A with multiplication star, and we have a rect homomorphism from A to the following set. We take out G, it's the group of automorphisms, and consider the conjugation quandle, we have a quandle. And on the Cartesian product, y it's equal to a's direct product and x, we defined the following operation. The first component is only operation in A, and now we have the action of an automorphism phi sub B on element A. And we proved with Victor Bovdi that with algebraic system, y with operation circle is erect. And in addition, if x and a are quandle, and phi a lies in the kernel of the map phi for any element a, when x with circle is a quandle. And we can define a semi-direct product where y with operation circle is said to be semi-direct product of x and a with respect to phi and is denoted by the following formula. And in particular, if a is the conjugation quandle and phi its identity map, when we have some analog of Golamur for the rect A, and we will denote it by whole X. And using this construction of semi-direct product, we can introduce the averaging operation with Victor Bovdi, and with definition it's the following. Let X and A be two rects, and phi is a rect homomorphism from A to conjugation quandle of odd X. The map B from X to A is said to be relative averaging operator on X with respect to phi if the following equality holds. And the quadruple is called a relative averaging rate. And now we have the following construction. Suppose that gamma sub B it's the set of pairs Bx and X. It's the subsets of semi-direct product. It's called the graphic of B. When we can define the product of two elements from the graphic by the following rule, when this product Li is gamma sub B if and only if the following equality hold for any element x and y. And we prove the following theorem. An operation B is a relative averaging operator on x with respect to phi if and only if gamma sub B is a subgraph of a semi-direct product. This theorem, it's analog of theorem which was proved in the paper of Zhang, Sheng, and G. In this paper, they introduce relative Rota-Baxter operators on group, which are generalization of group Rota-Baxter operators, and prove analog of the previous theorem. And we introduce a Rota-Baxter operator, and we averaging operator, and we study this operator. At first, if we take x is equal to a and phi is mapped from x to the group of inner automorphism, such that phi sub ba its symmetry in the point ba, when b, which satisfies the following equality, is said to be averaging operator on x, and the pair as and B is said to be an averaging rate. And now we can prove the following proposition. Let B an averaging operator on rex, and the circle is defined by the following formula. B a binary operator when x with this new operator is a rec, and if in addition the following equality hold when x with this operator is a quandle. B is averaging operator on this rect, and B define a homomorphism from this rect to this rect. You can see this is analog of result which was proved in the forward group. And it's interesting to formulate the following problem. You remember, if we have a group, we have operator, Rota-Baxter operator on group, when we can construct new group operator and we have a skew brace. And is it possible to define this analog of skew brace for the rec? Because we have two operators. We defined the Rota-Baxter operators by the following formula with Victor Bovdi and study the property of this Rota-Baxter operator. It has the following properties. This is example of Rota-Baxter operator. At the end of my talk, I want to formulate the following question, which is interesting. Suppose that we have a Rota-Baxter group, under which condition we define a Rota-Baxter operator, or maybe averaging operator, on the conjugacy quandle, or on the core quandle, or on the generalized Alexander quandle. This is connection between group Rota-Baxter operator and the Rota-Baxter operator, or maybe averaging operator, or rec. That's all. Thank you for your attention.
Well, thank you very much for your very nice talk. Are there any questions in the audience?
I have a question. May I ask?
Yes, please go ahead.
Hi, Valerie, thanks for the talk. So I'm wondering whether averaging operators also give solution to the Yang-Baxter equation?
Yes, it's a very good questions, but we did not study this because see, it's not understandable which operator is more interesting, averaging operator or Rota-Baxter operator. Because by the property, averaging operator is look like as a group Rota-Baxter operator. Of course, it's interesting to understand the connection with Leibniz algebra, because we know connection group Rota-Baxter operators with Lie algebra, and we know connection of rec with Leibniz algebra. And it's interesting to understand connection between Rota-Baxter operators on this algebraic system.
But the group Rota-Baxter operators give solutions to the
Yes, you are right. But here, I don't know.
I see. Okay. So when you say you want to count the averaging operators or Rota-Baxter operators in various categories, so you have some equivalence, right? You want to count modulo some equivalence. Like we know we can define isomorphism of two Rota-Baxter operators. That means an isomorphism of groups making the diagram commute. So you have some definitions like this in the setting of Hopf algebras and racks and quandles?
No, because see, we only define these operators. Also, I remember some paper where people introduced averaging group. It's look like as a Rota-Baxter group. But we only introduce this definition, have found some very elementary properties, but did not study it deeper.
Yeah, thanks.
Valery, thank you for your talk. I have a question. How can you translate quandle and rack to Russian? Because I saw Google Translate, it's for quandle, it's quandle, and for rack, it's like stoika.
See, it's an interesting story, because quandle, when Joyce defined this object, he have found some words without meaning. Because, you know, if we have a group not only algebraic object, it's some collection of people. But quandle, as I understand, does not have another meaning. And because Matveyev also introduced this object, and Matveyev says that this is self-distributive groupoid. But what is rec? Rec, yes, I know some meanings. It's rakovina, something like this. But in Russian, people usually say quandle and rec.
Okay, thank you.
Okay, thank you.
Okay, thank you very much. And I guess we can thank again the speaker, and we will have a small 5 minutes break before the next talk. So thank you very much again for the talk.
Okay, thank you. Thank you for your attention. Thank you. Bye bye.